And thanks to the organizers for putting together this really nice workshop, very interactive. It's really nice to be here, part of this, very active group. I think I need a pointer. Actually, I have one. I can grab my own. Okay, so I'll tell you about some recent work, which we call the Anomalous Hall Crystal, and I think it has some very interesting connections to both to experiment as well as to some fundamental theoretical ideas, thinking about quantum crystals. So hopefully I'll be able to make both these connections in this talk. But this is a very important slide. These are my collaborators on this project. So Junka and Tomo are both at Harvard. Dan moved recently to a faculty position at UC San Diego, and these are our Berkeley colleagues, Mike Zaltal's group, Taiga, and I think Tianla is here somewhere in the audience. Okay, so let me sort of take a step back, and before we start talking about crystals, I'll tell you something very simple, or kind of remind you about this very simple picture of insulators. So you're thinking of a periodic crystal. You have an insulator, and there are two sort of opposite ways of thinking about it, two dual perspectives. One is this atomic picture, where you have electrons localized at certain sites, and that gives you an insulator. The dual picture is in momentum space. You completely fill a band, and you end up getting this band structure, which has a gap. And the two can be related in many cases by the Wannier relation. You take the bands and make them into atomic orbitals. Okay, but there are cases where you cannot do this. So these are really the topological phases, and this obstruction is interesting. So, one of the sort of paradigmatic phases is the Chern insulator. So you have a solid which has this band structure. It must have edge states. That's really the topology of these bands. Okay, and the fact that you have these edge states requires you to have a certain degree of entanglement, and that's really what gives you this obstruction to recovering the atomic insulator. Okay, so if you were to make a cut in real space, divide your system, look at the reduced density matrix, it must have a spectrum that reflects the edge state that you would get if you had a physical edge. Okay, so this implies you can't really, shrink your atomic wave functions down to the wave functions of the insulator. The Wannier functions cannot be shrunk into these point-like objects if you have a hope of recovering a non-trivial entanglement spectrum that looks like that. Okay, so it's ultimately related to the entanglement in these non-trivial insulators that you have this obstruction going from the band picture to the atomic picture. Okay, there's another way to think about this, which is in terms of using symmetries. So this is not required to get these Chern insulators, but it's very useful sometimes to diagnose the Chern insulators, and we'll actually maybe briefly mention this towards the end. So imagine you have some symmetry like rotation symmetry, C2 rotation symmetry. You can go to certain momentum points in the Brillouin zone which are invariant under that rotation. For example, the gamma point or these high symmetry points, and you can label them by the symmetry eigenvalues for rotation plus or minus. And for example, you may, for a single band, you may find this kind of assignment, and it turns out that this is really a fingerprint of a Chern insulator. This particular assignment where you have an odd number of minus orbitals versus the plus orbitals. Okay, and what you can show is that if you had an atomic insulator, if you could think of your electrons as simply being localized at certain sites, of course, it's just a single band, so it has to be localized at C2 invariant locations in the unit cell. So those are the Wyckoff positions. You can easily convince yourself that the corresponding assignment of symmetry eigenvalues in momentum space would have to have an even number of minus, the even proportion between the plus and minus. Okay, so it's impossible to get something like this if you insist on thinking of the electrons sitting in certain sites. Okay, so that's another way to see that there is no atomic picture for these Chern insulators. Okay, so now let me kind of switch gears and talk about quantum crystals. So the difference now is that we're going to think about the translation symmetry as being spontaneously broken. Okay, so we start with electrons in the continuum. Think of Coulomb interactions between the electrons, and there is a ratio between the potential and between the interaction scale and the kinetic energy, this RS, that tells you how important interactions are. Okay, and it gets bigger as you go to lower densities. What was shown many years back is that if the density is low enough, you can get this Wigner crystal phase where your electrons spontaneously break translation symmetry, and you can arrive at this conclusion starting from a classical limit. Think of the electrons as classical particles by switching off the kinetic energy, minimize the configuration, minimize the interaction energy, and then you can perturbatively turn on the quantum mechanics, the kinetic energy term, and you can argue that it's stable to quantum fluctuations. Okay, and what is seen in numerics is that starting from this infinite RS, if you like, where you switch off the kinetic energy, as you lower RS, it survives till RS is around 30 or so. Okay, so that's the Wigner crystal, and it has many interesting properties. For example, because it breaks translation symmetry, it has sound waves. It's gapless. That's why I'm talking about it in this particular conference. It's also compressible, so you can ask what is the periodicity of this Wigner crystal. Well, that changes, depends on the density of electrons. You change the density of electrons, it'll change its periodicity. You could, if you wish, take an alternate viewpoint on the Wigner crystal, which is not typical. You can think of the electrons over here as seeing a self-consistent field from all the other electrons. It's like a periodic potential. They're moving in this periodic potential. And there are bands, and they completely fill a band to give you an insulator. Okay, it's kind of the dual picture of this Wigner crystal. Okay, so self-consistently generated bands. Okay, so now putting the two parts of this, what I told you before, it kind of sets up the following question. So this is what John McGreevy calls the method of the missing box. So you have these three boxes, and you're trying to fill in the fourth one. So we talked about bands. We said there are trivial bands which have an atomic limit, and Chern bands, for example, topological bands which don't. We talked about crystals where there are Wigner crystals which have this atomic limit. And the question is, do you have something over here which is sort of a topological version of a Wigner crystal, which is actually what we call this anomalous Hall crystal. Okay, so you could have asked this question purely on the basis of theory many years back, but somehow I think it needed the prompting of the experiment for us to ask this question. Okay, so I'll tell you about this anomalous Hall crystal. But the reason for this name is we're thinking of a phase of matter which spontaneously breaks translation symmetry. So it's like a Wigner crystal. That's the crystal part of it. It spontaneously breaks translations. It spontaneously breaks time reversal symmetry. That's the anomalous part, like anomalous Hall. And it's also a Chern insulator. Hall, that's the Hall. Okay, and there are related phases, not exactly this, Hall crystals, which was introduced by these people. There they have a magnetic field that introduces the topology. It breaks time reversal. It sets a certain filling for your electrons as well. So that's a much more familiar setting. But the question is, can you realize a phase of matter that's sort of at the intersection here? Okay, and so there are different questions that come up. One is sort of a more philosophical question. If you look at these basic notions of condensed matter physics, Anderson talks about his view of solids, of quantum solids, where you think about the particles at different sites as being distinguishable. Okay, that's, I think, really this classical limit of a crystal, where you think of particles localized at certain sites. But how do you think about a Wigner crystal when you don't have such a Vanier representation? Okay, where you don't have such a classical limit. That's what we're talking about. That's sort of maybe more philosophical. And so I think you don't really need this sort of very extreme picture of a crystal. Okay, but maybe a more practical question is, where do you find it? Okay, can you actually create conditions where you can realize this the state of matter? Okay, and so what prompted us was this very beautiful experiment by Longzhu, which we'll hear more about in the next talk. In these rhombohedral graphene structures, the N-layer rhombohedral graphene, and there were 3 theory papers, one by Senthal's group, one by Yahui and collaborators, and one by us, came out roughly at the same time. And I'll tell you why we think these ideas may be relevant to this setup. Okay, so first, very quickly, let me tell you about rhombohedral graphene. This is the structure of rhombohedral graphene. It's we think of N stacks, N sheets of graphene stacked on top of each other, but in this rhombohedral fashion, where you take one layer and you slide the next layer and put it on top of it. Third layer is, slides again and put on top, so that you end up with this kind of stacking. The A of one layer is above the B sublattice of the second layer, okay, and so on. Okay, and so this is a very interesting structure for topological bands, because if you just stare at this structure, just look at one row of one column of atoms, you have a hopping within the layer, which is the usual graphene hopping. If you expand it around the Dirac node, it's VF times K. You can think of K as a complex number. And then there's a hopping between the layers, this T1. So it's really like a staggered hopping model, like the SSH chain. And if you're in the regime where this VFK is not very big, then you are in some topological phase, effectively for this 1D chain, where the low energy modes are on opposite sides of the stack. Okay, the 0 modes of the 1D chain. This is kind of a hybrid representation where Kx and Ky is sort of suppressed. It's like a parameter, and this is the z-axis stacking. Okay, so the low energy states are these 0 modes on either end, and in the experiments, what is done is you take 5 layers of this and put on an electric field. So these 0 modes get split. They have opposite potentials applied, and you get these rather flat-looking modes, dispersing modes on either side of this graphene sheet. Okay, so that's really what we'll start with, and this is really where the experiments are looking at. They're going to be partially filling, this band over here, for example. Okay, so that's the experimental setup. I won't talk too much about it because Long is going to talk about it. So there is a vertical electric field. On one side, there is a HPN substrate that's aligned with the graphene sheets and gives rise to a moire. So there is some moire in the problem, but the electrons turn out to be on the opposite side of the stack. Okay, so so electrons are on the moire distant side, and the question is, what happens in this setting? So you can look at this in theory first. And ask, is it possible to get a churn insulator in this setup? And we have sort of a lot of experience now getting churn insulators in these moire systems. The way it usually works is that you have this valley degree of freedom. You have sort of a valley spin Hall or a valley Hall insulator to begin with. In the opposite valleys, you have opposite churn numbers. And the role of the interactions is kind of like a Hund's or an exchange coupling. All the electrons go and polarize into one valley. Okay, that's typically what we have seen before in many of these moire systems. So you can try to see whether that works over here. You could assume that you're in a single valley and look at whether this distant moire over here can actually give you a churn band. Okay, and what all of us have found is that it's too weak to really separate out a band. You get some modification, but it's all still part of the continuum of bands for electrons on this side of the device. Okay, so this simple explanation that works in many of the other, like in the TMD MOT2, twisted MOT2, many of the other twisted graphene structures doesn't seem to work. But in experiments, what Long and his Group C is a clear indication of a Chern insulator. Okay, so they see, so this is a function of the density of electrons. This is of 1 electron per Moray unit cell, this vertical line, and this is the strength of the electric field that's being tuned. And these are typically larger than what people used before for these multi-layer graphene sheets. Okay, and there's a very clear insulator over here, which has a quantized Hall conductance. There are also these fractional features that I'll talk about later. So, but very crudely, the phase diagram is it's metallic on the right. It has this quantum anomalous Hall over here, and it's got a high resistance state on the left, which you can think of as a Wigner crystal. Okay, so so this is, I won't talk too much, but they see hysteresis, spontaneous breaking of time reversal symmetry near this nuclear 1 regime. They see good quantization of RXY and very low RXX. And there's a phase diagram over here. You tune in density or you tune in displacement field. You go from this quantum anomalous Hall insulator into the metal, for example, or into some other insulating state. Okay, so this phase is clearly present, although the naive expectation you don't see it. So the question is, why do you get this Chern band even in this Moray distant regime? Okay, so the solution, at least according to us, to all these papers, is that it's really interactions that are crucial not only in polarizing the electrons, but also in generating these Chern bands. Okay, and so if you, for example, what we did is we just looked at Hartree-Fock. We kept many of these bands, and you project the Coulomb interaction into this band structure, and you see this very nice Chern 1 band separating out when you're at filling of 1 electron per unit cell. Okay, so interactions, they not just polarize spin and valley, but they also seem to generate these Chern bands. Okay, so the gap is really set by the interaction scale rather than by the Moray scale. Okay, so then the obvious question is, what if I start lowering the Moray potential? Does the gap survive? How does it scale with the Moray potential? Okay, so this is what this is showing. So this V1 is the strength of the Moray potential. You get some particular gap, and then let's say you make it a fraction, and you see the gap doesn't really change. The same color code over here. And of course, the question we asked ourselves is, what happens if you completely switch off the Moray potential? Okay, and it turns out that the gap remains the same. So really, within this Hartree-Fock, you don't need a Moray potential to seed this breaking of translation symmetry. It wants to break the translation symmetry. Okay, and you can compare its energetics. Even in the absence of a Moray potential, you find that the energetics of this crystalline state is better than the metallic state as you tune the vertical electric field. Okay, so this is really a case of a spontaneous translation symmetry breaking, but this band that you get, the self-consistent band, has Chern 1. Okay, so it's an example of a topological band that's created by spontaneous translation symmetry breaking, so the anomalous Hall crystal, okay, at least within this Hartree-Fock approximation.
They should have any density to the question.
Yeah, yeah.
At any density, you would get the Chern crystal.
So there's a range of densities. It couldn't be any old density, but there's a range of density. It's not like the fixed, exact commensuration with something. Just like a Wigner crystal, you can get Wigner crystal of a range of densities. Not any density. There's a preferred range, but yeah, Una.
How do you understand why this is happening?
Yeah, I'll talk a bit about that if I have time, or you save it for the end.
Okay.
Yeah.
Is 5 layers some magic number?
No. So I'll show you a phase diagram. You can get it with 4 layers, or you can get it with 6. What changes is the displacement field at which you get it. So if you go to more layers, you need a smaller displacement field. You go to fewer layers, then you need a larger one, which is, you could get it in tri-layer perhaps, but the displacement fields you required to apply are kind of, not reasonable for experiment.
In theory, you could just get bilayer.
Bilayer is different, I'd say. Yeah, bilayer is kind of extreme. Yeah.
In the range which you call metal, do you still have value polarization?
Yeah, so it's a spin and valley polarized metal. So if you, yeah. Yeah, just actually that's true in the experiment as well. You can see this part is in the metal, and it has an anomalous Hall effect. You see it as finite RXY. Yeah.
There's a locking of electron density to the crystal lattice.
So there is an underlying lattice of carbon, which is at a completely different scale compared to the electron densities over here. So the electron densities here is much lower than the atomic densities of carbon.
Yeah, no, I'm not.
Right.
I mean
the Morey potential.
No, not the Morey potential. So if you squeeze, let's say there's zero Morey potential.
Right.
In this, like, if you squeeze the anomalous Hall crystal, there's
Yeah.
some of the flux or.
It will remain a crystal, but just with a different period now. And it remains Chern 1. So yeah, we'll talk a bit more about the properties about, many of these properties are just the same as Wigner crystal, except for the fact it has a Hall effect.
The Morey potential should still play some role here because this total Hall region is only observed at U equals to 1, right? And U equals 1 is invariable against the Morey.
Yeah, so if you have, it's like a ferromagnet and a magnetic field, right? If you have a very tiny field, you will still polarize the ferromagnet. But if you have a fairly strong field, you're definitely polarized. You're not going to get something in the opposite direction, right? So the experiment is being done with the Morey potential. We think it's weak, although it's hard to quantify. But do the thought experiment where you, let's say, make the Morey potential 1/2 of what it is. The prediction will be that the gap is not changing. The single particle gap is not changing, which is different from the Morey-dominated regime where the potential is set by the Morey. The gap is set by the Morey potential. Yeah.
Do you expect the same physics if there is no Morey potential if it's at a large angle at the bottom?
That's a very good question. We'll get to that. In this simple picture, so this is a Hartree-Fock approximation, right, which overestimates the order. If you believe this holds all the way, then even in the absence of a potential, you should get this physics, but there's always disorder. So there is a symmetry breaking field, which is, things like disorder that are present. But if you could make it pristine, completely clean, yeah, you should, essentially get the symmetry breaking without the Morey potential. Yeah.
So the time versus symmetry is already broken.
Yes.
So you have spin and value polarization.
Yes, exactly. Yeah. Yeah, but the translation.
So it's not the fact that time versus symmetry breaking is spontaneous. It's somehow if you're getting turn 1.
Yeah, right. Yeah, so this question about the densities. So this is, roughly speaking, a phase diagram. This is simplified so that, this is the actual computed phase diagram. At large density, you get a metal within this Hartree-Fock, spin polarized and value polarized metal. At small densities, you get the regular Wigner crystal, Chern 0. And there's an intermediate range of densities where you get the anomalous Hall crystal. And that's seen over here as well. This is the computed phase diagram, low density Wigner crystal, anomalous Hall crystal, and metal. Okay, roughly speaking, that is what is seen in the experiment. Yeah. Good question. So it's not a particular density, but there's a range. What is setting this? So it turns out this density is roughly the same argument for the magic angle and graphene. It's the same ratio of constants coming in. So this separation between this unit cell distance, that's the thing shown over here. 12 nanometers, that's roughly the Morey scale and magic angle graphene. So it's the ratio of the interlayer coupling to the in-layer hopping. That sets it, yeah.
So in the original Hall crystal of discrepancy property, so there you have an external field.
Yes, so there you have an external field, and for example, what could happen is you have, let's say, an equal to 1, and then you add electrons. It's not an equal to 1 anymore, but those electrons can Wigner crystallize and give you an equal to 1 state. That's my understanding of the Hall crystal.
But there, that state is flux follows if you compress it, you change the electron density, and that somehow
Yes,
not locked to the flux.
that's right. So there is already there's a magnetic field that kind of sets a length scale, although it doesn't break translation symmetry in the usual sense. It sets a length scale. Here, there is nothing like that. Here is just the continuum. Yeah, so it is quite different, I would say, compared to the.
Still bonons there, right? So if the
Yes.
field is fixed, and you change the Wigner crystal, we compress the Wigner crystal, it's compressible, right?
Yes, yes, without any pinning, yeah.
But nevertheless, mu is 1, so there's somehow...
Yeah, so you shouldn't think of it as nu. That's, nu is always the reference to something else, like either magnetic field or Moray. You should just think of it as the Hall conductance. And to get this quantized Hall conductance, you have to pin the crystal. Just like for a Wigner crystal, it's not insulating unless you pin it. So there's some weak potential that pins it, and then you get the Hall effect, the quantized Hall effect. Okay, so these points I think already we made over here that the Moray gives you a potential. We don't know exactly how strong. It could be, for example, that the actual electron liquid is not a crystal; it's metallic, but but it's close to becoming a crystal. It's near a transition, and the Moray pushes it over into the phase. Or it could be already in the phase, and this is just a pinning field. It could be stabilized at different densities over a range. It has a gapless Goldstone mode, sound waves, essentially, 2 of them. And what is most interesting for us is that it actually seems to be a very good mechanism for creating churn bands. Okay, so usually in this game, in this Moray, churn band kind of setup, a lot of things have to go right in the microscopic model for you to get the churn band, and it's sensitive to microscopic details. Here, a lot of these further neighbor hoppings, T2, T3, and so on, do not seem to matter. At least when we do the Hartree fork, we get pretty much the same phase diagram. It's also predicted for different number of layers. So 4 and 6, the critical vertical electric field you need turns out to scale with the number of layers. It's smaller for a larger number of layers. Yeah.
So the phonon mode, is it going to get some chirality?
Yeah, that's a very good question. Let me talk about it at the end. We were confused about that. I think that's the main fundamental question in this problem. What is the spectrum of the phonon modes? But let's discuss it at the end. Okay, so actually I've lost track of the time.
So yeah, it's another 15 minutes, but because there's questions.
Yeah, so I'll try to end in 5. Okay, so actually the the experiment also saw fractional states. And we can reproduce that, although not in a super convincing form, because what we do is we project all the interactions into a single conduction band. Okay, so this goes against our philosophy that the Moray is weak. But given the limitations of what you can do, you can't really do Hartree fork to get fractional states. If you have to do any of these numerical calculations, we can only work with a single conduction band. And there we do see, for example, in equal to 2/3, we see the expected fractional quantum Hall state. One sort of intriguing possibility this whole thing raises is, could you have a fractional anomalous Hall crystal? Okay, so let's say you're at a density where you're outside this yellow region where you get the anomalous Hall crystal. You're at a lower density. Instead of forming an integer quantum Hall phase with the nuclear 1 kind of periodicity from the self-consistent lattice, you may actually want to create a lattice for which the electrons are at, say, 1/3 filling. And then spontaneously fractionalize and get the Laughlin state. This would be an example of fractionalization in the continuum. I think conceptually it's certainly possible. The question is, how do you convincingly demonstrate it in a microscopic model, given the kind of things that we can do? So that's sort of a kind of left for the future. And finally, let me just mention, we have now a fairly simplified understanding of the energetics leading to this phase. So this is really what the dispersion looks like. I showed you before of these 0 modes. If you look at the wave functions of these 0 modes, they kind of propagate down into the stack. So when you're at k equal to 0 right at the Dirac node, it's a 0 mode at the top layer. And as you move away in momentum from the Dirac point, you get this ratio. This is what I talked about. This is the same thing that appears in magic angle graphene. So this ratio rises as you go away from the Dirac point. And we're at densities where this ratio reaches about 1/2 or 1. Okay? And then there is a spinner, layer spinner, if you like, the wave function of the 0 mode. And because of the spinner structure, you get some Berry curvature. Okay, so this band over here, it has this pretty flat dispersion, but there's also some Berry curvature. and that is really what seeds this quantum anomalous Hall state. Okay, so in the density range of interest, there's roughly about pi Berry flux through the band. And then if you take, so these are different densities over here for the orange lines. If you kind of fold these, this dispersion, you get this band. And this is sort of the empty lattice approximation. You fold everything, but you don't open up any gaps. And this is the range of the interaction, the strength of the interaction. These bands inside this gray shaded region are going to mix and hybridize. And you can focus, if you like, just on this K point where there are 3 plane waves that are degenerate. Okay, and if that, so the interactions will mix and split them if the state that is picked is the right angular momentum combination under this rotation. Just like we did for the symmetry indicators for C2, you'll end up getting a churn band. And the fact that you have churn flux inside to begin with sort of kind of favors this in certain regimes. Okay, so we have a simple, it's called a 3-patch model. We literally just look at the gamma and the K points, and we can tell when you're going to get an anomalous Hall crystal, when you're going to get the Wigner crystal, the C equal to 0 state, and when it's going to be metallic. Okay, so let me conclude. Okay, so one of the interesting questions that arises beyond Hartree-Fock, how do you think about anomalous Hall crystals? You don't have this classical limit that you can go back to. We know Hartree-Fock overestimates Wigner crystals. In fact, for the conventional Wigner crystal, the RS value is numerically found to be 30. In Hartree-Fock, it's like 1 or 2. Okay, so it overestimates the range of the range of stability. How do you do that for the anomalous Hall crystal? Could it be we're also overestimating it over here? We probably are. But it turns out, one piece of good news is that this anomalous Hall crystal for certain parameters is stable over a very wide range of interactions. Okay, so if you say Hartree-Fock is overestimating the stability over here with weak interactions, or if the actual anomalous Hall crystal is reduced, there's still a big range where we can work with. Okay, and you can also talk about what are the experimental signatures. If you have a sliding anomalous Hall crystal, what does that give rise to? And can we extend this 3-patch mechanism to other platforms? Okay, but maybe I'll stop over here.
Yeah, so if I create a dislocation of the Wigner crystal, so does that carry any non-trivial quantum number at all? Or?
Not, and so let's just talk about the difference between anomalous Hall crystal and Wigner crystal. Properties that are different between the two. I don't think there's anything new that arises for anomalous Hall crystal.
Yeah, but so what is?
That's not the topological response. It's not some coupling between the translation symmetry and the charge. But yeah, we are looking for something like that. If I find something, I'll be interested. Okay. But so far, we have not. Actually, this goes back to Zenbi's question. What about Goldstone modes? Are they different? And it's actually a very interesting question because for Wigner crystals, you have 2 linearly dispersing modes if you ignore the long-range Coulomb. But if you put on a magnetic field, they combine into a single quadratic and a gap mode. So the question is, which one does this fall into? And it's not obvious actually, because like in a magnetic field, it breaks time reversal. But there's no applied magnetic field, so in that sense, it's like a Wigner crystal. So that's we actually know. I think we know the answer, but it'd be good to confirm it with calculations.
Since you're doing Hartree-Fock, there's got to be a simple way to understand this, but I'm not getting what the simple way is. So is it in any way a little bit like P-wave superconductor? For instance, so there you get a gap by having a superconductor, and you have a band structure which may or may not have Chern number. So you get a gap here doing Hartree-Fock. In that gapped band structure, you may or may not have Chern number.
Yes.
Right?
Yeah.
Is there a similar kind of, can we think of this in an analogical, in sort of in analogy, like that transition between having churn zero and non-zero?
Yeah, so that's what we were hoping to answer with this kind of 3-patch model. I think this is where it gets closest to trying to answer that question. So first of all, it cannot be super universal. It depends on parameters, because we could get churn 0, we could get churn 1. And roughly speaking, the simple-minded criterion is how much periflux do you have in the Brillouin zone. So if it is too little,
in the bare band structure before you turn on interaction.
And that depends on the density, roughly. If the density is very low, you don't actually realize this Berry curvature in the Brillouin zone, and you end up locking into the churn 0. But as you increase the density, you see more of the momentum space, and then you pick up. Once you get to around pi Berry flux, it tends to pick up the combination, which is the one that gives you the churn band. Now, if you go to even larger densities, it turns out dispersion kicks in, and you end up getting a metal. So that's kind of the simple-minded interpretation of the phase diagram.
I have more questions, but I'm going to let other people ask.
Okay, probably a question about the same 3-patch model. So 2 related questions. One, whether it's the same interaction when you get churn band, you also get valley polarization within the same model. And second, what sets the width of the churn band?
Yeah, that's a good question. So in this calculation, we kind of assume the spin and valley polarization.
Only by hand?
By hand, yeah. When we do Hartree fork, it always happens, and experimentally it's always seen. So the challenge here was to go from the continuum. So we never apply a Moray potential over here. It's all self-generated. So we wanted to focus on that aspect. And the width of the churn band, that's a good question. I think it's, the bands are pretty flat over here to begin with. And then you separate out this churn band. But the actual dispersion of that churn band, I don't have a simple formula for what that dispersion is. That's a good question, actually.
So in this three-patch picture, the order parameter of the Wigner crystal, is it like constant or is it momentum dependent? So can you say like if this density wave is just as in usual Wigner crystal, or is some kind of a D wave or P wave or whatever? Is there momentum dependence to it?
Yeah, that's a good question. So, for the, in terms of the shells, right, it's roughly a sinusoidal kind of potential. So you only have to look at mixing with the first, with the first reciprocal lattice vectors. Now, this question about the form factors, it's kind of related to picking out the right combination over here of C3 eigenvalues.
Yes.
But I don't know how to translate it into the kind of form factor you want.
Okay.
But it is that, the potential that picks out the angular momentum 1 or minus 1 at the k and k prime points, rather than the angular momentum 0. So that, I think it can...
So it may be non-trivial, actually. In this.
Yeah, it may be non-trivial, or it's the band itself is supplying the non-trivial winding for the spinners. I don't know. There's something to think about there.
Yeah, so the result currently shown on the phase diagram only has turn numbers 0 and 1, right? So is there any sort of fundamental reason why higher turn number doesn't sort of show up?
So actually, I didn't put up the references. There's a paper by Senthil and collaborators similar to this 3-patch, and they talk about, maybe there are regimes where you could get higher churn, but it's not as stable as this. In our model, once you get beyond, some amount of Berry curvature, the dispersion kicks in. And then it's kind of, it's not going to be insulating. You could get more Berry curvature, it's not going to be insulating.
So mostly it's some energetic reason that may or may not be universal. Well, likely not universal, I suppose.
Well, if the question is, could you get higher churn anomalous Hall crystal? Definitely yes. If you can get churn 1, just make many layers of that, right? But in this setting, could you do it? Not clear, yeah.
Yeah, I just wonder about the transition between the Anomalous Hall crystal and the Wigner crystal. And does disorder play an important role in that?
Yeah, that's a good question, actually. You could imagine it's a purely topological transition where the underlying lattice just goes through and you have Dirac cone and then it reopens. Yeah. Or, as you said, like an integer quantum Hall transition. I think in our numerics we see first order. It kind of flips.
I see.
But that may be the the method, right?
But if it was second order, maybe the phonons would play some role, coupling
Could
in.
be, yeah.
Possibly.
Yeah, it could be interesting, yes. Although, is it really that different from a solid, which is, solid is also a quantum solid, right? It's just we think of them as different degrees of freedom, but there are phonons there too, and they could interact with your, with the low energy degrees of freedom at the transition. There may be separation of scales, so it's not important. But
Yeah.
It's very, very short.
I can catch up.
okay, yeah.
Yes, so thank you very much. Yeah.